Hello and welcome to Lecture 40 of my class from Data to Decisions. This is Chris Mack, your instructor for this class, and in this lecture we're going to be using R and Excel to generate some autocorrelation functions and to perform the Durbin Watson test for autocorrelation of our residuals, and finally to do some remediation to apply an AR1 model to our linear regression. Let's begin with the autocorrelation function. Here in Excel, do this manually using the correl function. So here is correl or correlation function in Excel. I give it an X and a Y, two data sets. And to create an autocorrelation of a set of residuals compared to a lagged version of the residuals, I simply shift the data down by one. So the first set of values, array 1, will be all of the values from 9 to 107, so first 99. And then the second set of values, C10 to 108, is the second to the 100th data point. And so I'm correlating a set of data with a set of data lag 1. And when I execute that, I get this 0.535 correlation. Well, I can do the same thing, but a lag of 2. So now I do the first 98 and the last 98 data points, and I get a correlation coefficient of 0.15. I can keep doing that with a lag of 3, a lag of 4, etc., all the way down to a lag of 10. And if I plot all of these together, I get what's called the autocorrelation function, or ACF. By definition, the autocorrelation function is 1 for a lag of 0, because something is always perfectly correlated with itself. So I just type in the number 1 in that cell, but then I plot all the rest. What does this look like to you? Well, you have to remember that when the autocorrelation function gets close to 0, we can get differences from 0 just due to randomness. So these kind of small autocorrelation values are not statistically significant from 0. So we see these kind of oscillating up and down, maybe even go negative occasionally. Down here, these are all just about 0. Right? This one is not. It's bigger than 0. We're going to be able to test for that. And if we really had an AR1 model, really had an AR1 behavior, rather, in this data, what do we expect? We expect the second 2 lag autocorrelation value, lag of 2, to be equal to the autocorrelation for a lag of 1 squared. Lag of 3 will be lag of 1 to the 3rd power. So this is 0.535. If I were to square that, I get 0.28. Instead, I get 0.14. So it is lower, but probably not statistically significant difference. In any case, I think the assumption of an exponentially decaying autocorrelation function, which is what an AR1 model predicts, is supported by this data. We'll come back to that if we were to try to correct for that or something. We would need to know that. Let's look at another set of data. This is sunspot data. The number of sunspots observed in the year 1770, the year 1771, etc. This data is in the data sets on the website. And what do we see? If I again do the autocorrelation, I find that there's an extremely high autocorrelation with a lag of 1. So just about 80% of the number of sunspots in 1 year is correlated or can be explained by the number of sunspots in the previous year. And the other 20% is just randomness. If I go to a 2-year lag, well, it looks like it's less, right? And a 3-year lag, it's getting close to 0. If I keep going, look what happens. This is falling down like it might be exponential, but then it goes negative. Then it turns up and it goes positive again. And then it goes negative again, then positive again, and it oscillates. And so it looks like a sinusoidal variation that has exponential envelope. Well, this simply means that there is this autoregressive kind of behavior on top of a cyclical behavior. And if you know anything about sunspots, you know that there's an 11-year cycle. And we see that because it reaches the peak again, 11. So sunspot data cycles at about a 10 or 11-year cycle. And we can see that very clearly by looking at the autocorrelation function. Let's apply some of these concepts to a linear regression. Here's some linear regressions we've seen in the past. I've got the calibration data for a flow meter, liquid flow meter, but it's a special one because it's flowing liquid nitrogen and measuring the flow. It's being calibrated, and we see that this calibration curve is a function of temperature. So at different temperatures, you get different readings, different errors in the reading of our flow meter. And that's what we're trying to do in this experiment. So the question is, are the residuals of this linear model independent? So we do a best fit, calculate the residuals. So here I'm showing the data minus the equation for my linest results, which are over here, and I get a residual. If I look at the lag plot, there's the sequence, residuals versus run number. If I go over here and look at the lag 1, I do see a correlation. Maybe it's 0.35. Is that statistically significant, or is this maybe just random noise? I see some couple of large values over here that might be driving it, but even without that, maybe there's still some correlation. We have to test. We have to decide whether a correlation coefficient as low as 0.35 really is significant. How do we do that? We do it with the Durbin Watson test. Bert talked about that in the previous lecture. A Durbin Watson test looks at the difference between a residual and the prior residual, takes that and squares it, and looks at the sum of the square errors or differences in a residual and its prior value. So I have this table of those squared differences between a residual, D10, and its previous value, D9. And then I calculate the Durbin Watson statistic here. I get 1.1. Recall that small numbers mean more positive correlation. A value of 0 would mean I have perfectly correlated residuals. A value of 2 means perfectly uncorrelated residuals. Numbers bigger than 2, the Durbin Watson statistic, implies negative correlation. So this is a number that's definitely smaller than 2. It's closer to 1. But is it small enough to be statistically significant? Well, to do that, we have to compare it to some critical values. In the tables that I've put on the website for the class, you can look up some critical values. For example, here is critical values based on alpha of 0.01. Now recall that we don't have an exact critical value. Instead, we have a range of critical values. We have a lower and upper limit. The lower limit here is 1.237. The upper limit is 1.337 for an alpha of 0.01. And for this number of data points and this number of parameters in the model. All of those things affect the critical values. If the Durbin Watson statistic were greater than 1.337, that is closer to 2, that means uncorrelated. And we would not be able to reject the null hypothesis that our residuals are uncorrelated. However, if we are less than the lower critical value, lower limit, that means we can reject the null hypothesis that the residuals are uncorrelated. And in fact, that's what happens here. We have 1.17, 1.116, rather, 1.12, and our lower limit is 1.24. So we do get a value less than the lower limit, and therefore we can, with alpha of 0.01, reject the null hypothesis that the residuals are uncorrelated. All right, what do we do? Normally, we would try to search out the source of this autocorrelation. Generally, if we're trying to do experiments where we don't want to see a time dependence, we're trying to the temperature dependence, after all, not the time dependence in our data. We would go and try to improve the experiment. However, in some cases, we want to include the time dependence in our model. And if we do that, we can use a transformed model. So we can do an autoregression transformation. What does that mean? We talked about it in class. It means we're going to shift or transform the x values and the y values by taking, for every x value, we will take that value and then subtract off correlation times previous value. Right? So our correlation is 0.389 for this data. It's just the correlation with a lag of 1 for all of the data. Notice that the other methods we talked about, the slope and that equation, in this case, both of them are less than using the correlation to estimate rho. Nonetheless, we'll use this correlation as our estimate of rho. And so the transformed x will be the x value minus this correlation, H4, times the previous value. Likewise, transformed y will be the y value at trial 2 minus y value at trial 1 times this correlation. We will then do a linear fit of y prime as a function of x prime. So here I show a plot of the transformed y versus the transformed x, and if I do a straight line fit, I get a different model, obviously. Notice that the slopes are essentially the same. They're not exactly the same because I actually have one less data point in the transformed data than in the prior data. But we expect those two values to be, in fact, the same. The intercept, however, changes. What also changes is the error estimates, the standard errors about those parameters. And now we've got standard errors that are valid because the assumption of uncorrelated residuals we hope is now true when we do our ordinary least squares regression on the transformed data. So the transformed data allows me to calculate new values of the slope and intercept by transforming them back. So I take the intercept of our new fit and divide by 1 minus the correlation that I used, 1 minus rho, a rho estimate, and that gives me minus 11.56. You see, it's not really much different than minus 11.53 that I got originally. So in fact, I have not changed the intercept and slope values by doing this transformation. What I have changed is the standard error estimates for the intercept and slope. Let's take a look. The original linest gave me intercept and slope standard errors shown here, and the transformed values are shown here. And in particular, we see a little bit of a difference, a little bit larger standard error for the slope than we had originally, but a smaller standard error for the intercept than we had originally. So these are going to be better estimates of the standard errors, and therefore we'll have better estimates of the confidence intervals. Now, once we've done this transformation, we can get a whole new set of residuals here. We need to test those to find out if we really have gotten rid of the correlations in our residuals. So we'll do another Durbin Watson test. And so I'll do a second Durbin Watson test on the residuals of the transformed model, and you can see I get 2.36. Much closer to 2. The p-value is going to be very high for this statistic. We have successfully removed the correlation in the residuals. In fact, we may have removed them a little bit too much. We have a slight negative correlation in our residuals. It comes from maybe estimating a value of rho that's too high. Right? Notice we have other estimates of rho that we could have used. This one maybe is too high. What if I lowered it? Let's just give it a try. I know that if I put in 0.25, I know what's about to happen because I've done it before. If I used an estimate of 0.25 instead of 0.39, I get slightly different values for slopes and intercepts, but again, transformed back, they're not really much different than they were before. Our Durbin Watson statistic now is exactly 2. Yeah, I did this before, so I know the answer was going to be 2. This is the value of rho that gives me exactly perfectly uncorrelated final residuals. In fact, if I look at the correlation of these new residuals, you see it's almost exactly 0. Whereas before, when I was using 0.39, the correlation of my residuals with a lag of 1 is in fact minus 0.25. That is, I introduced some negative correlation. I overestimated the correlation of rho. Correlation rho that I was using for my autoregressive 1 model. So that's how we accomplish the task of determining whether an autocorrelation exists using the Durbin Watson test and what to do about it using Excel. We can accomplish the same things in R. In fact, it's quite a bit easier. Let's go to R. Here's a script called Durbin Watson test.r, and I will read in the data for the flow rate calibration, just like we had before, and we can plot that up, create a model, summary of that model, and put a best fit line. So this is just our generic modeling of a set of data. Now we can also do the lag plot just as we saw before and ask, does that really exhibit positive autocorrelation? Well, there's a couple of things we could do. There's a test called ACF, which I'll show you in a moment. But we can also just do the Durbin Watson test directly. So there's a package called LMTest. If you haven't installed it, you need to install that package. We've used it before, so I will just implement the library, and then I will run EW test of the model. So that's all I have to do. Once I've done a linear model up here, and I created something I called model, which is the best fit line of flow difference versus temperature, I can use that model directly by throwing it into this routine called DW test. When I run that, it runs the Durbin Watson test. It gives me Durbin Watson statistic, 1.116, and a p-value, probability that the true autocorrelation is greater than 0. Just by random chance is 0.001. So a small p-value below our alpha, and therefore we can reject the null hypothesis that the true autocorrelation is 0. Let's quickly go back to Excel. Let's see, what value of Excel did I get? Well, there it is, 1.116, the exact same number as I'm getting here in R for the same test. Well, that's good. What if we want to do something about it? Well, we first need to estimate rho and evaluate whether or not we think an AR1, an autoregressive lag 1 model, is appropriate. And here I'm going to use a function called ACF. All right. I'll supply the model residuals to this function, and it will generate a plot and some statistics. So the plot is autocorrelation function plot, just like we saw before. A lag of 0, obviously 1. There's a lag of 1, 2, 3. The dotted lines here show me the range over which autocorrelation values between those two dotted lines are not statistically different from 0. at some, I believe it's 95% confidence. But we do have one value larger than these limits, and so that is a statistically significant row. What row value is it? Well, I can pull it out with this command. You have to go in and see exactly what the format of the output of this ACF function is, and if you do that, you'll find that this is how we'd extract the autocorrelation lag 1. And I get 5.3 number, and that's the estimate that this algorithm provides for correlation lag 1. Now, if we wanted to, we could use that number to create transformed data. I don't know, maybe there's some routines that somebody else has written that will automatically transform the data. I didn't find it. I didn't look that hard. I decided I was going to do it myself. So here I'm going to use a for loop and perform the transformation manually. So I'll calculate the length of the array, model residuals. Well, it's the 39 data points. Then I'm going to set up two arrays. I'll call them y prime and x prime. And I'm just going to fill up arrays with values of 0. How many values? 38. I'm going to do n minus 1 because our transform data will be one shorter than the original data. So now I have these two arrays that are filled with zeros. I'm going to fill them up with the true values that we need, the correct values for our transformed data. To do that, I'll do a for loop for I in 1 to n minus 1, so 1 to 38. I will assign to y prime the flow difference of data point 2 minus r times the flow difference of data point 1, increment up through all of the data. Same thing for x prime. When I execute all of that, I now have all of the data I need in the transformed coordinates. When I plot the data, see the plot just like I've seen it in Excel. I can now model it. So I create a new model of y prime versus x prime, which if I look at the summary, I see the exact same values for the intercept and slope. If I were to use the exact same value of r, I would get the same values as I got in Excel. I can put the best fit line through there, pull out the slope and the standard errors and convert them back just like we did before in Excel. And finally, I can run the Durbin Watson test on the new model. And sure enough, the Durbin Watson test is a little bit bigger than 2 because maybe I went a little overboard on the value of r. Well, this is how we would do testing for autocorrelated residuals in R and in Excel. As always, things are a little bit easier in R, and that would be my preferred approach to do it. But if you like using Excel, you can look at the Lecture40 Excel spreadsheet on the website. Well, that's it for our autocorrelation and autocorrelated residual examples. Next lecture, we're going to start a major review of everything we've done so far. Till then.